Hello, everyone. Welcome to this lecture about thermodynamics. This is to make up for the class that I wasn't able to be in person. All right, let's get started. So here's my strategy with this chapter. I want to skip all of the, most of the theoretical stuff, I would say, that you can read the textbook and find out, and instead do a more problem-solving oriented approach to this chapter. I'll give you the tools that are just necessary enough to do the problems efficiently. And of course, you have lectures with your professor to go over the more theoretical aspects. Okay, so having said that, let's get started. This chapter has three main quantities that you'll be dealing with. You have what's called delta H, you have what's called delta S, and you have what's called delta G. So the three quantities actually are H, S, and G, but we'll only be interested in changes in these quantities. Delta H is the change in enthalpy. Delta S, is the change in entropy. And lastly, delta G is the change in free energy. Enthalpy deals with heat. Entropy deals with disorder. And delta G deals with spontaneity. Okay. In this chapter, you'll be looking at these three quantities in two separate contexts. The first is the context of formation, and the second is the context of a chemical reaction. So a formation is technically a chemical reaction, but it's a particular kind of chemical reaction. When we talk about formation, we mean how much enthalpy, how much entropy, and how much free energy change is accompanied with the formation of a compound. So for example, pick any of your favorite compounds. I'll do C6H12O6. This is glucose. Associated with the formation of glucose. So to form the compound glucose, let's say a mole of glucose, you have some amount of enthalpy associated, some amount of entropy associated, and some amount of delta G associated. All of these quantities are denoted by the formation subscript. So delta HF, delta SF, and delta GF. Okay. You have seen this before, but the superscript, this superscript symbol stands for standard. And in this chapter, standard will be 25 degrees Celsius, 1 atmospheric temperature of pressure, 1 atmospheric pressure, and that's it. That is what standard means in this chapter. So you can have standard enthalpy of formation, standard entropy of formation, and standard free energy of formation. The F represents formation. And so you get each of these values, enthalpy formation, entropy formation, and free energy of formation for any given molecule. That said, what would you think would be the formation values for elements? Because for compounds, it's clear. Yes, compounds are formed when elements combine with each other. But what combine to give elements? Nothing. Elements just are, for the sake of this chapter, right? So the enthalpy of formation, the entropy of formation, and the free energy of formation are all zeros for elements. So delta HF, delta SF, and delta GF equals to 0 for the case of elements. Now, a chemical reaction has a bunch of players in it, reactants and products, most of whom usually are compounds. Some of them might be elements, but many of them are compounds. So now you can ask a separate question. what is the enthalpy change, entropy change, and free energy change associated with a chemical reaction? And those are simply called delta H reaction, delta S reaction, and delta G reaction. So formation is for compounds, reaction is for the whole reaction. And there is a very nice relationship between chemical reaction and formation, and this is how it goes. The enthalpy of the enthalpy of a reaction is given by the sum of the enthalpies of formations of the products minus the sum of enthalpies of formation for the reactants, multiplied by appropriate coefficients. The appropriate coefficients being the coefficients from the balanced chemical equation. So multiplied by what we would call stoichiometric coefficients. Okay. This formula applies exactly in the same way to delta S and delta G. So what this provides us with is a very nice modular sort of method to figuring out the reaction values from the formation values. So delta S formation for the products minus sum of the change in entropies for the reactants. Same thing, multiplied by stoichiometric coefficients. And lastly, delta G reaction, same deal. Okay. Here's an example. Determine the pick one, enthalpy, entropy, free energy, doesn't matter. Let's go with free energy, the delta G reaction, and let's say this is evaluated at standard conditions. So if you're trying to calculate the standard reaction values, then you need the standard formation values. And if you're trying to calculate the non-standard reaction values, then you need the corresponding non-standard formation values. But let's go ahead with this question. Determine the delta G reaction for the following reaction. Let's burn some glucose, C6H12O6 plus 6O2 gives 6CO2 and 6H2O. These are balanced. And you're given the following information. The delta G formation of C6H12O6, let's say, is negative 500 joules per mole. I'm just making up some values. And you're given that the delta G, well, let's say these are standard values since we're asked for the standard reaction value. Delta GF for CO2, let's say, is negative 100 joules per mole. And delta GF for water is, let's say, negative 50 joules per mole. So given these values, delta G, standard of the reaction, will be, remember, it's products minus reactants multiplied by coefficients. So it's going to be, first product, carbon dioxide, delta G formation, standard of carbon dioxide, 6 times, because there's the coefficient of carbon dioxide is 6, plus 6 times the formation free energy change for water, minus 1 times delta GF standard for glucose, C6H12O2. We have minus now because we're now in the domain of reactants. So products get positives, reactants get negatives, and all of them are multiplied by their appropriate coefficients. If you notice, I've given you the delta G formation values for every species in the chemical reaction except one, and that has to be oxygen. I haven't given you that value because we know what that value is. For elements, all of the formation stuff is 0. So minus 6 times delta GF for oxygen, which is just 0. Okay, let's plug in our values. 6 times for carbon dioxide, I've given it to be negative 100, plus 6 times water is negative 50, minus 1 times for glucose, I've made it to be 500. And so the value here is negative 600 minus 300, I think, plus 500, which comes out to negative 400, I think. Great. That's how you calculate the reaction values from the formation values. Same goes if the question was calculate the delta H reaction or delta S reaction. You would do the same thing, products minus reactants, and everything is multiplied by respective coefficients. Cool. Having done this problem, let's move back to the 3 quantities that we encounter in thermodynamics and talk a little bit about what their sign represents. So you've got your delta H, you've got your delta S, and you've got your delta G. And specifically, let's talk about this in the context of a reaction. So you're given a chemical reaction, and you're given the 3 values associated with the reaction, delta H, delta S, and delta G. And based on the sign, the 2 possible signs of these values, you can say something about the type of reaction that you're looking at. Let me see if I can erase this. Okay, so the 2 possibilities are your reaction could be negative or positive. If your delta H is negative, then the reaction is called exothermic, meaning the reaction releases heat. And as a consequence of the reaction releasing heat, the temperature rises. If your delta H is positive, then the reaction is called endothermic. In endothermic reactions, energy is absorbed by the chemical system, and as a consequence, the temperature is reduced. In the case of delta S, a negative sign indicates, a negative value indicates that the disorder decreases, and a positive sign on delta S indicates that disorder increases. In the case of delta G, a negative value indicates that the reaction is what's called spontaneous, and a positive delta G indicates that the reaction is non-spontaneous. Okay. Delta H is pretty self-explanatory. It simply tells you whether the reaction releases heat or absorbs heat. However, the case of entropy is a little more up to imagination. Disorder is all about how jumbled up your system is. The more jumbled up, the more mixed up your system is, the higher disorder it has. And so we can come up with a couple qualitative metrics to understand, to sort of predict if entropy goes up or down. For example, mixing always increases entropy. For example, imagine you have your initial system where a bowl has sand in it and another bowl has salt in it. So sand and salt, separate bowls, two separate substances. And then you mix them up, and that is your system 2. Now, the question is, which system has greater entropy? Well, the system where we've mixed the salt and the sand has greater entropy because of the fact that it's more jumbled up. It's harder to tell salt from sand. They're all mixed up. So mixing, as a general rule of thumb, always increases entropy. Going from gas to liquid to solid, it's the other way around. Going from solid to liquid to gas increases entropy because solids are compact. All the molecules or the atoms are at a fixed or relatively fixed distance from each other. They're not moving around like crazy. Everything looks like it's sort of like an ordered army. That's what we call a lattice. It's very orderly. Liquid, it has a little more degrees of freedom. The molecules are able to slide past each other. So there's a little more movement, a little more chaos. And in the case of gases, everything goes haywire. All the particles are just flying around like crazy. And so gases have the highest entropy. So melting of water is an example of an increase in entropy. Condensation, going from vapor to liquid, is an example of a decrease in entropy. It goes without saying that if a process has a certain direction associated with one of these values, delta H, delta S, and delta G, then the reverse process has the reverse values attached to it. So if delta H is positive in one direction, then it's negative in the other. If delta S is positive in one direction, then it's negative in the other, and so on and so forth. Which is to say, if you flip the reaction, then delta H, then delta S, and delta G flip their values, i.e., they change their sign respectively. If they were negative, they become positive. If they're positive, they become negative. Okay, so mixing increases entropy. Going from solid to liquid to gas increases entropy. If you're dealing with gases in particular, a reduction, if all that happens, and I should stress on this, if all that happens is that the volume gets bigger, then the entropy goes up. Conversely, if the volume is shrunk, then entropy decreases. This is assuming that temperature has remained constant. Very important. If temperature changes, then you have to take other effects into account. For gases, if temperature goes up, entropy still goes up, because if temperature goes up, then each molecule of the gas has more energy than before, and so it's going crazier than before. It has a higher average speed, it is doing more collisions, and it's just buzzing around faster. I think that's about it when it comes to predicting whether entropy increases or decreases qualitatively. Delta G is a very important quantity, and it tells you whether your reaction is spontaneous or not. Spontaneous means that your reaction proceeds as soon as you mix in your reactants without any further help. It is ready to go. For example, if you ever mixed vinegar and baking soda, you notice that the fizzing starts immediately upon mixing vinegar and baking soda. You don't need to heat the mixture up, you don't need to spark it, you don't need to do any extra, you don't need to put in any extra effort to get it going. That's what a spontaneous reaction is. If when you mix the reactants, the reaction doesn't proceed automatically, then that kind of a reaction is called non-spontaneous. It needs a little bit more encouragement. This encouragement can come in the form of the reactant mixture needing some amount of heat before it gets going. Spark is an example of providing heat. For example, gunpowder If you have a bowl of gunpowder, it's not gonna catch on fire and explode. Even though gunpowder is combustible and there's plenty of oxygen in the air, so the reactants are in contact with each other, but the reaction is not happening until you provide a little bit of spark, which is when the reaction gets going. We'll understand more of why certain reactions need encouragement and what that encouragement formally is for a little bit further down in the chapter related to something called activation energy. But you understand qualitatively what it means for the reaction to be spontaneous and non-spontaneous. Keeping in line with what we've talked about before, if a reaction is spontaneous in one direction, then it's non-spontaneous in the reverse direction. Conversely, if a reaction is non-spontaneous in a specific direction, then it is spontaneous in the reverse direction. You flip the direction, the sign of each of these values flip, and so the interpretation flips. Okay. Now, these three quantities are all connected to each other via this very important equation called, I think it's called Gibbs formula or something. I might be mistaken. But these three quantities are connected to each other via this formula. Delta G equals delta H minus T for temperature times delta S. Super duper important. One thing you should gather from this equation is that if you know the change in enthalpy, and you know what temperature the reaction is being carried out at, and you know the change in entropy, then you can automatically calculate delta G. As in, delta G, delta H, and delta S are not independent quantities. Delta G is determined by delta H and delta S. In fact, it is a definition. It is defined this way. Okay, having said that, let's do something really interesting and also really easy. We know delta H can have two possible signs, positive and negative. We know delta S can have two possible signs, positive and negative. Let's make a chart out of all possible combinations of the signs of delta H and signs of delta S and figure out what it says about the sign on delta G. So we can figure out in what instances is the reaction spontaneous, in what instances is the reaction non-spontaneous, and in what cases the reaction might just need a little bit of encouragement to get going. So remember our goal. Our goal is to turn delta G negative. If delta G is negative, then the reaction is spontaneous. If delta G is positive, then it is non-spontaneous. Now, delta H, remember, has two sign possibilities. Delta S has two sign possibilities. That is a total of 2 times 2, 4 possible combinations. Temperature, on the other hand, this is Kelvin temperature. And if you remember, Kelvin temperature is always positive. So you can't change the sign on T. It's always positive, no matter what the temperature is. The lowest that temperature can get to is 0, but otherwise it's positive. Okay, let's make up a little chart and write down all the possible sign combinations of delta H and delta S. I'm going to start with negative and a positive here, case 1. Delta H positive, delta S negative, case 2. Both positive, case 3. And both negative, case 4. These are the 4 possible sign combinations for delta H and delta S. And now let's see what it leads to delta G having a sign of as a consequence. All right, let's start this game. Remember, delta G is delta H minus T delta S. Plugging in the signs, delta H, I've, in this case, chosen to be negative, minus temperature, as we remember, is always positive, and delta S, in this case, is a positive number. So this simplifies to a negative minus positive times a positive is a positive number. Now, what is this? This is like -5, -3. A negative number minus a positive number. This is what it looks like. Well, what's -5 times -5, -3? -8. What if I switch them up? -3, -5. Still -8. So it seems like in this case, the answer will always turn out to be negative. Always. So the interpretation that goes with this is that the reaction is spontaneous. In fact, reaction is always spontaneous in this case, which means that the reverse reaction is always non-spontaneous. Okay, great. We have our first case and interpretation. Second case, delta H is positive minus T times delta S. Temperature is always positive. Delta S I've chosen here to be negative. So this simplifies to a positive number minus positive times a negative is a negative number. And this becomes two negatives make a positive. So this part just turns out into a positive number plus another positive number, which is always going to be a positive number. So delta G in the second case is always positive. So the reaction is always non-spontaneous. In the third case, we have delta H positive minus temperature, which is always positive, and delta S also positive. This time, I get a positive number minus a positive times a positive is yet another positive. So this is what this case boils down to. It's a subtraction of two positive numbers. Now we've got to be careful here, because if you have a positive number and you're subtracting another positive number, it can go either way. For example, 3 minus 5 is -2, which turns out to be a negative number, and 5 minus 3 is +2. So depending on the relative size of the first positive number and the second positive number, the overall sign can go either way. So in this case, it is ambiguous. But suppose we want the reaction to be spontaneous. Suppose we want to derive the condition for spontaneity. Let's try and rig this calculation so that the answer comes out to be negative. Well, to do that, remember, spontaneity requires delta G to be negative. So we want this overall thing to be negative, which means we want the second term to dominate so that the second positive number is a bigger number. How do we make that happen? How do we make the second term dominate? Well, look at what the second term is composed of. Temperature and delta S. If you're given a specific reaction, the delta H, delta S, and delta H and delta S are unchangeable. So you're stuck with those values. However, the only external knob that you've got is the temperature. You can change the temperature. Well, how do I make the second term dominate? If I make temperature really large, then the second term starts to balloon higher and higher. And that's how I make the second term blow up, dominate. So spontaneity seems like happens when the temperature is high enough. Okay, so the interpretation in this case is that the reaction is spontaneous at high temperatures. Last case, delta H is negative, minus temperature is always positive, and delta S is negative. And so you get a situation where the first term is negative, a positive times a negative is negative, and so you have a negative number minus another negative number. This is two negatives, so that becomes a positive. Negative of a negative is a positive. So it boils down to something that looks like this. You have a negative number that's being added to a positive number. Once again, the answer can go either way, so it's ambiguous. For example, I can have -2 plus 1, which is -1, a negative number, or I can have -2 plus 3, which is +1. So the answer can go either way. Once again, this is ambiguous, but once again, similar to case 3, we want to play the same game. We want the overall thing to be spontaneous, and so we want the second term, we want the overall thing to dominate. Now look at what happens here. The first term here turns out to be negative, which is what we want, and the second term is fighting that negative. So in this case, for the overall thing to be negative, we want the second term to be as small as possible, because we don't like that term. Well, you can do that by dialing down the temperature low enough so that this second term becomes minuscule and the first negative term wins, making the overall delta G negative. And so the interpretation here is that the reaction is spontaneous at low temperatures. There it is. The first two cases where the reaction is strictly spontaneous or non-spontaneous, and you can't change it from spontaneous to non-spontaneous or vice versa by changing the temperature. Temperature has no effect in the first two cases. The second two cases, encouragement works. You can make the reaction go from non-spontaneous to spontaneous by controlling your temperature knob. All right, last part of the chapter, some miscellaneous things related to entropy. The first thing is that the entropy change of the universe equals the entropy change of the system plus the entropy change of the surroundings. Questions to imagine from this kind of an equation is you're given the delta S of the system, delta S of the surroundings, calculate delta S of the universe, you would just add them up. Or you're given the delta S of the universe, delta S of the system, and asked to calculate delta S of surroundings, and so on and so forth. Basically, you're given two values and asked to find the third one. And the second thing, which is that the delta S in each case, delta S of the system, equals heat divided by temperature of the system, and delta S surroundings equals heat divided by temperature of the surroundings. These two heats here, let me distinguish them by calling them one Q system and the other Q surrounding. If you're imagining a closed system, or not even, if you're imagining a system that is absorbing or releasing heat, then it must be releasing or absorbing that heat from the surroundings. If your system gains heat, let's say if your system gains a Q system amount of heat, then that heat it gained by sucking it in from the surroundings. And if your system releases Q system amount of heat, then that heat gets dispersed into the surroundings. So that is to say that the Q system and the Q surroundings are always equal in magnitude because the exchange is happening between the system and the surrounding, but opposite in sign because one's absorbing, the other's releasing, right? Another way to say the same thing is that one is absorbing heat at the cost of the other losing heat. And so that is something to remember. In these terms, I can rewrite this equation in the following way. Delta S of the universe equals Q system divided by temperature that the system is at plus Q surroundings divided by the temperature of the surroundings. All right, and that covers pretty much the entire theory in the chapter. that is essential for problem solving. Let's look at a couple problems to top this off. Here's the first one. Suppose you're given a chemical reaction. Let's call it C6H12O6 plus 6O2 gives 6CO2 plus 6H2O. And you're given the delta H formation values and the delta S formation values, all its standard conditions for all of these. I'm just going to make these up. -500, -200, -120, and let's say here this is -70, -20, and -50. So here's all the information that you're provided, and you have a series of questions. Calculate delta H reaction standard. Oops, there shouldn't be a question mark there. That's good. Calculate delta S reaction standard. And lastly, calculate delta G reaction standard. The first two are straightforward and is a very simple application of calculating the reaction values given formation values, something we've seen before. So this is products minus reactants multiplied by coefficients. So in the first two cases, the delta H reaction will be 6 times the given value of -200 plus 6 times the given value of -120. Let me specify their units. Suppose this is in joules per mole Kelvin. Joules per mole Kelvin. Let me just write it out. That's the unit of entropy. And for enthalpy, let's say that these values are in kilojoules per mole. This is often something that happens that you see in thermodynamics questions. There's a joule unit mismatch between the two flavors of quantities that are given to you. For example, there's a unit mismatch between delta H and delta S. One is in kilojoules, the other one is in joules. Let me just, for the sake of simplicity, go ahead and make these -700, -200, and -500 joules per mole. So what you want to do is either convert everything into kilojoules or everything into joules. I'm going to go with the simpler converting joules to kilojoules. So this is going to be -0.7 kilojoules per mole, -0.2, and -0.5. Converting to kilojoules would involve dividing by 1,000, which is what we did. Okay, let's complete our delta H calculation here. 6 times -120 for the product. Okay, we're out of products. Coming back to the reactants, 1 times -500. And oxygen is an element, so I can forget about it. And so I get -1200 minus whatever that is, and plus 500. So let's say that this comes out to some number. Let's call it number 1. And it is in kilojoules per mole. Then we come down here, do the same thing with delta S reaction. 6 times -200 up. Make sure to work in kilojoule units now. So -0.2 plus 6 times water is -0.5. And now it's reactants, so negatives, -1 times -0.7. And for the oxygen, I can forget about it. And so this comes out to some other number, let's say number 2 kilojoules per mole Kelvin. Lastly, to calculate delta G reaction standard, well, I'm not given the formation values, so we'll have to rely on the answers in part A and part B for delta H and delta S. Lucky for us, we have a reaction connecting delta G to delta H and delta S as follows. This is the reaction that we've seen before. And now it's all about inputting the numbers. So this is number 1 from here minus, what would be the temperature? So unspecified temperature in this question. But the hint is you're doing this at standard conditions, which is 25 degrees Celsius. But the temperature in the formula is in Kelvin. So make sure to convert that into Kelvin by adding 273.15. That goes there. Times delta S reaction, which is this number that we have calculated up here. And you're done. Another question. A certain reaction has a delta H reaction standard value of, let's say, negative 100, and delta S reaction value at standard conditions at negative 200. Let me put some units on these things. Joules per mole Kelvin. Immediately off the bat, notice that delta H and delta S have a unit match because both of them are in joules. So I can use the numbers as given. Okay. And the question is, determine the range of temperatures at which this reaction is spontaneous. In fact, let me go ahead and reverse these values, and I'll explain to you why. A little bit later. Whoops, let me make this a positive. So both positives. Okay, so I see that the question says that the reaction is spontaneous. Spontaneity, my mind jumps to delta G, and the reaction needs to be spontaneous, so I know what that means. My delta G needs to be less than 0. Since we're talking about a reaction, I'm going to put my appropriate subscript, reaction, and since we're in standard conditions, there's the standard symbol. Okay, am I given my delta G? Nope. What am I given? Delta H and delta S. That's all I have. Well, we recall that delta G can be written in terms of delta H and delta S as follows. Delta G reaction at standard conditions is delta H reaction at standard conditions minus T times delta S reaction at standard conditions. Since I want my delta G to be less than 0, it means that this whole expression needs to be less than 0. All right, let's go ahead and plug in our numbers. 100 minus temperature T times 200. We demand that to be less than 100. Now, this is an inequality in the variable T. Solving an inequality is very much the same as solving an equality with one crucial difference. You can do everything that you do when solving an equation with solving an inequality with this major distinction. If you multiply or divide by a negative number, the inequality flips. and we'll see that in action in this case. So I have 100 that I want to get rid of. I'm going to go ahead and subtract 100 from both sides. So that cancels. Negative t times 200, I can write that as negative 200t less than negative 100. And now to isolate my t, I'll need to divide both sides by negative 200, which means I'll need to divide by that. And as a result, since I'm dividing by a negative number, the inequality flips. So temperature greater than negative 100 over negative 200, which is positive. Negative over negative is a positive. Positive 1/2, which is 0.5 Kelvin. So above a temperature of 0.5 Kelvin, this temperature is spontaneous. And that's our condition. So the range of temperatures is basically 0.5 Kelvin all the way to positive infinity. So if we draw a number line for temperature, and here's 0 because the Kelvin temperature scale ends at 0, but it goes on indefinitely. Then at 0.5 Kelvin and beyond, that's the green area. That's the spontaneous area. Which means that any temperature below 0.5 all the way to 0 is the non-spontaneous area. Now, what do you think happens at 0.5 Kelvin, at the boundary? Well, it's the boundary between spontaneous and non-spontaneous. And what happens at the boundary, and some of you might be pleasantly surprised, is that the reaction is happy. It doesn't proceed at all. It just stays there because the reaction is at equilibrium. So at the threshold, at the sharp boundary between spontaneity and non-spontaneity, the reaction is at equilibrium. In fact, there is an equation that connects the most important quantity from equilibrium, K, to the most important quantity in thermodynamics, delta G, together. I don't know if it is covered in this chapter or if your professor has covered it. I'm just going to put it here. It goes delta G standard for a reaction is equal to minus R, ideal gas constant, times temperature, times the natural logarithm of equilibrium constant K. Beautiful little equation. Of course, since this is thermodynamics and all we're dealing with is energies, R should be the energy kind of constant, which is 8.314. Some units of joules and then some other stuff that I forget. Okay. Let's make up a question with this newly introduced equation, just in case it is on the chapter. Question 3. If delta G reaction standard equals minus 25, calculate K. Okay, a very simple application of the formula above. This is in joules per mole. Joules per mole gives you negative 25 equals negative 8.314. This is standard, so 298.15 Kelvin times the natural logarithm of K. All right, let's divide both sides by this mess. this thing equals ln of k. Now your k is trapped inside the function ln. Well, what is the arch nemesis of the ln function, i.e. what is its inverse? It will be the exponential function. So raise both sides to e, and that kills the ln. And so k equals e to this whole mess. Let's call that some number, e to that number. That's it. Easy question. On a qualitative level, delta G and K are related as follows. If your delta G is negative, it means that K is greater than 1. If your delta G is positive, well, that means that K is less than 1. And at the boundary in between, when delta G is 0, K equals 1. So this is the this is sort of like a range relationship between delta G and K. And I think you should see a question pop up on Alex that tests you on this. Remember, G goes with 0, K goes with 1, and the inequalities run in opposite directions. One trivial thing that I have forgot to put before we ended our theory discussion is if you add two chemical reactions, or let's say you add a series of chemical reactions, then their delta G's add up, their delta H's add up, and their delta S's add up. So addition goes with addition. If you flip a chemical reaction, this you know, then each of these flip sign. There's a third one. If you multiply a reaction by a certain number, then the delta G, delta H, and delta S all get multiplied by that same number. Okay, that concludes our discussion on thermodynamics. See you next Thursday in class.